Today we will discuss about the BPHCT-135 Block 2, which includes the zeroth law of thermodynamics and the first law of thermodynamics, along with some basic definition about the thermodynamical system, processes, so and so. So now I start with presenting my topic, thermodynamical first unit. In unit 5 we learn about thermodynamic description systems. See, so thermodynamic description of systems. First of all, we have to know what is a system. A system is the space under study, a region of space under study. These systems also categorized as it may be homogeneous or heterogeneous system. Homogeneous system where the chemical composition are uniform, and in case heterogeneous system the chemical compositions are not uniform. Now see, a region of space under study is the system and everything else around it is the surrounding. And an arbitrary surface enclosing the system is called the boundary, right? About the system, we know what is a closed system and open system. A closed system exchanges energy, not mass, with the surrounding. But in open system, both energy as well as mass are exchanged with the surrounding. That means system exchange energy and mass with the surrounding in case of open system. Similarly, your boundary, that is the imaginary surface, there is no surface separating the system and surrounding. Okay, suppose you were learning about a gas which is enclosed in a chamber, right? So your study is only open on the gas inside the enclosure. So we may say that is this is the your gas is your system, and regarding everything outside this gas, they are the surroundings. So when this gas exchange with the surrounding, you might have been observed many things. When a hot body, when a body is placed upon on the burner and kept outside, and you bring it outside and place sometime, you see its temperature falls. Where its temperature, why its temperature falls? Because it's radiate energy to the surrounding. That is why its temperature falls. So this is how they exchange or energy and mass with the surroundings. Boundary, we have a dithermal boundary, adiabatic boundary, rigid boundary, permeable boundary, semi-permeable boundary, so and so boundary. So if a boundary allows exchange of energy or heat, that is diathermal or thermal boundary. That is, it is thermally conducting. Adiabatic boundary does not allow heat to flow through it. Similarly, a rigid boundary which cannot be moved. A permeable boundary allows matter to flow through it, and a semi-permeable boundary allows some constituents of the system selectively to flow through it, not allows all this matter to flow through it, only selectively some. Now see, thermodynamic variable. The macroscopic quantities, pressure, volume, temperature, internal energy. About internal energy we will learn later. Okay. that determine thermodynamical state of a system. They are called thermodynamic variables. As a pressure is volume, temperature, they are the macroscopic, not microscopic. You cannot say the pressure of molecule, pressure of gas, which contains large number of molecules. So that is why this is macroscopic. Microscopic is the atomic, subatomic level, only molecule level. When a mass of molecule is considered, that is a macroscopic quantity. Simply, when you temperature of gas, not temperature of a single molecule. So macroscopic quantities. They determine the thermodynamic state. You can say, suppose your system is the gas in the chamber. What is the pressure inside, pressure of the gas? What is the volume of the gas? What is the temperature of the gas? This is the thermodynamic state. So these variables are known as thermodynamic variables. Thermodynamical variables, they may be extensive or intensive. Okay, the extensive variables, they depend on the mass of the system, and the intensive variable do not depend upon the mass. Suppose pressure, temperature, they do not depend upon the mass. So they are intensive variable. Whereas the mass, volume, they depend upon the mass. So they are extensive variable. Now go for equation of state. This is the mathematical relation among thermodynamical variable. Okay, for a particular process, that is in thermodynamic equilibrium. So mathematical relations among thermodynamical variables, that is P, B, T, so on. We know PV equal to RT in thermal equilibrium. That is a equation of state. Similarly, other equations are there relating to pressure, volume, temperature. These equations or relations, they are called equation of state. Now, thermodynamic equilibrium. We can say a system is in thermodynamical equilibrium when it's simultaneously in thermal, chemical, and mechanical equilibrium. When the system is thermal equilibrium, the temperature of the system and surrounding are same. There is no flow of heat, right? Similarly, in chemical equilibrium, there is no change in the density or chemical composition. And when the system is in mechanical equilibrium, the net force torque upon the system is zero. That is when whole this when whole the three a system is in simultaneously three equilibrium, that is say thermodynamical equilibrium. Thermodynamic process. So when a system undergoes a change, its thermodynamical variables, pressure, volume, etc., they undergo a change. That is called thermodynamical process. Okay, so change of one or more variables, that means thermodynamical variables. We say at a time one variable changing or two variable changing or more than two variable changing. Okay, so this is called thermodynamic process. Okay, we'll learn about the isothermal, adiabatic, isochoric, isobaric. We'll tell which variables are changing in these cases. Okay, then reversible process. Reversible process, a system and surrounding, okay, performed in such a way that at the end of the process, both system and surrounding on their initial state without producing any change in the rest of the universe. That means when a system undergoes change, okay, undergoes change, and at the conclusion of the process, the initial state of the system is same. Initial state is represented by this pressure, volume, temperature. Suppose the initial state was the pressure is P1, temperature is T1, and volume is V1. When the system undergoes a change, that means the pressure, volume, temperature, or any one of them changes. So after so many steps, when we reach at the final state, we see the pressure, volume, and temperature of the system is are same, P1, V1, T1. So if a process is not reversible, if this is not satisfied, then we call irreversible process. Actually, practically what we observe in the nature, many processes are irreversible process. Okay, there is very few example of reversible processes, and this when a process takes slowly, if there is any loss of heat, then the process cannot be reversible. The process cannot be reversible. Okay, because any process is followed by a diagram or path that is called in the indicator diagram. So indicator diagram, this is a diagram between pressure, volume, right? So when a system undergoes some changes, the pressure, volume changes, and we will find so many points on the pressure volume graph, and when we join them, we will get a curve. That curve represents a process. Okay, and the area below this curve represents the total work done during the process, right? When some heat will be either evolved or heat will be rejected to the surrounding, in that case the same path cannot be followed, and we cannot may not reach at the end of the process, we may not reach at the initial state of the system. So reversible process, the initial state, that means very simply we can say the initial state, final state, they are same. Okay. Then quasi-static process. If a process carried out in such a way that at any instant the system departs only infinitesimally from an equilibrium state. Okay, so if the system departs infinitesimally from the equilibrium, that is called quasi-static. If there is a finite departure from the equilibrium, then this is called non-quasi-static phase. Of course, I have not written here that since in your book there is no mention isothermal process, adiabatic process. In isothermal process, the temperature of the system remains constant, pressure volume undergo change, pressure volume changes, pressure volume change, but the temperature remains constant. But if the pressure, volume, temperature all are changing, that is called adiabatic process. In isothermal process, there is exchange of heat. So the heat of the system doesn't remain constant. But in adiabatic process, where the temperature change, there is no exchange of heat. So the heat remains constant. Heat of the system remains constant. Okay, in adiabatic process. Similarly, in isobaric process, the pressure remains constant. Isochoric process, volume constant. We'll go through it. Now we'll let you know about the zeroth law. Now see, if we have two systems A and B, we have three systems A, B, C. A and B, they are separately in thermal equilibrium with system C. Okay, so if A and AB, they are separately thermal equilibrium with system C, then A and B are also in thermal equilibrium. Okay, This is very common. Many cases it is common, but not in many cases. So in this law, zeroth law gives the definition of temperature. Okay, how? Now, when the three systems are in thermal equilibrium, A, B, C, what is common? What is common in these three? The common is their temperature. So we say temperature is the common property of all the bodies in thermal equilibrium, or all the systems in thermal equilibrium. When the systems are in thermal equilibrium, they have a common quantity that is called temperature. Now see, the general equation of state for any gaseous system is this is a parametric form, FPVT equal to 0. That the function of, or a function of pressure, volume, temperature equal to 0. F is a single valued function of PVT. Right? Now you can say from this condition, you can derive these equations PVRT for ideal gases. For real gases, it is P plus van der Waals equation, P plus A by V square, V minus V RT equal to RT. So in terms of partial derivatives, now see the coefficient of isobaric volume expansion. Isobaric volume coefficient of expansion. Coefficient of expansion is the change in volume per unit volume for 1 degree centigrade temperature. 1 degree increase of temperature. Then change in volume per unit volume for 1 degree centigrade change of temperature. And when this thing is done at constant pressure, that is say, we say this is the isobaric volume expansion, and that is equal to a change in volume dV by V unit volume, then temperature is divided, that is for unit temperature at constant pressure. Similarly, isothermal elasticity, elastic elasticity, that is the coefficient of elasticity. It is stress by strain. Here we write here stress by volume strain. The stress gives a pressure also has the dimension of stress. You see, pressure is stress is the force by area. Force, or you can imagine restoring force per unit area or deforming force per unit area. Then force per unit area is also the pressure. Here change in pressure, change in volume. So for this change in volume, this is the change in pressure. Now change in volume per unit volume gives volume strain, and numerator you find the change in pressure. See, since this is done at constant temperature, that is why it is called isothermal elasticity. Now, compressibility. Compressibility is the reciprocal of elasticity. That is why 1 by Et, beta T equal to 1 by Et. So these thing alpha, Et and beta T, they are related to the change in pressure by the relation this delta P equal to alpha Et dt minus Et dV by V, where this Et equal to 1 by beta T we write there. Okay. Now in the next unit we go for the first law of thermodynamics applications.
Excuse me, sir. Sir, why compressibility and elasticity is in negative?
Because you see, when the pressure increases, the volume decreases. The change in volume means it is the final by initial. Okay, when we find the change is always final minus initial. When there is a decrease in the volume, the negative sign comes. Okay. When we exert pressure on a gas, suppose, what will happen to its volume? Its volume decreases. So its final volume is less than the initial volume. Then what is change in volume? Change is final minus initial, and initial is greater than the final. So this difference comes out to be negative. Okay.
Yes, sir.
So where there you see when you find in the negative sign in the derivative, that means C, that implies there is a fall, okay, or decrease in the value. Now see, the first law of thermodynamics. Before learning about the first law of thermodynamics and its application, we know some definitions. That is, see, heat is a form of energy that is transferred between system and its surrounding by virtue of temperature difference. We know it. So when there is temperature difference between the two systems, between the 2 points, between the two regions, the heat will flow from hot region to the cold region. And when heat is added to the system, that is taken as positive. And when heat is taken away from the system, that is negative. If an energy interaction takes place between a system and surrounding, not by way of difference of temperature, suppose there is energy interaction takes place between system and surrounding, not due to the temperature difference, the temperature same, but the energy exchange takes place, then we say that some work is done. Since work done by a thermodynamical system is positive, on the system is negative. The work done expression for different system. How could you find out the work done during a process or like expansion of gas? That expansion may be isothermal, may be adiabatic. So how do you find the work done? An analytic expression for the work done. Work done equal to the pressure and change in volume integration from initial volume to final volume. Now see how work done. Work done is the force into displacement, right? Force into displacement. And here pressure is force by area and volume is area into displacement. So area will cancel, that will give rise to the work done. Now see, when you exert pressure at constant pressure P, there is a change in volume dV, then pressure into change in volume give you the work done for this change in volume. And when you are to find out the total work done for the change from initial to final, then you have to make an integration over PdV. Okay, I'll show you now. See, isothermal expansion of a perfect gas. I write the final expression. What will be the expression for isothermal expansion? I will show. I copy some thing from the book. I'll show the expressions how it is derived. Now see, W equal to nRT logarithm is a base is exponential e ln nRT ln Vf by Vi. I'll show the expression how we come from this expression W PdV Vi Vf2 from nRT ln Vf by Vi, right? We'll show it. Now see, work done by or on the system during a process as well as heat absorbed or evolved by a system during a process are path dependent. Path dependent. I have already told you the process is described by a path in a PV diagram or indicator diagram. Okay, because when a process takes place, the state of the system undergoes various changes. So, for every state of the pressure and volume. When the state of the system changes, then pressure volume changes. So for every pressure volume, value of pressure and volume or order pair of values of pressure and volume, you will find a point. And when so many points you get and join them, you get a curve. And the area below this curve give you the work done. That is very important. When the exact relation between the or equation of state is not known and you are to find out work done, in that case this PV diagram or you say the indicator diagram is very useful, because the work done is the area below the curve, right? So when the work done by the system or on the system, in that case work changes. When work changes, the area changes. When the area changes, the path changes. That means work done depends upon the path. So work heat depends upon the path. They are path dependent. So they are not the function of the state of the system. Now see, another definition we know, that is the internal energy of a system. The internal energy of the system is sum of the energies of all molecules, atoms of the system. It is difficult to actually calculate what is the internal energy of the system exactly, but we can determine the change in internal energy, because change in internal energy is the work done. That is why we can measure change in internal energy the precisely, but not the exactly the internal energy. You see, the now we go for the first law of thermodynamics. The first law of thermodynamics states, if we give if heat can be given to a system and it is able to do the work, the amount of heat given to the system is equal to the change in internal energy and the external work done by the heat. So in mathematical form, we can write del Q equal to du. Du is the change in internal energy, U is the symbol for internal energy, and change in work done. This is the first law of thermodynamics. Now, Mayer's formula, we have already told it in the block 1. Cp equal to Cv plus R, or Cp minus Cv equal to R for 1 mole of gas. Now, using first law of thermodynamics, we can derive this formula. Okay, so I'll show you as some expressions today. The equation of state of an adiabatic process. The equation of state will going to derive this equation of state of adiabatic process, that is Tv to the power gamma minus 1 constant, Pv to the power gamma constant. This gamma is a symbol have their usual meaning, that is pressure, volume, temperature. And gamma is the ratio of specific heat, that is Cp by Cv. Okay, we show some. Now see, work done in an isothermal process. Now see, okay, W equal to PdV integration. You see, in book there is direct expression here. W equal to PdV integration, PdV, right? As you find PV equal to nRT. Okay, so since temperature is constant, is a isothermal process. For 1 mole of gas, you can PV RT, no problem. So what will be equal to P? P equal to RT by V, nRT by V. nRT by V, this is the expression of pressure we put here. nRT by V into dV. Okay, this nRT, they are constant. They can be taken out of integration. Now see, okay, so dV by V, the integration dV by V is ln V, ln V, and when you put the limits, the upper limit Vf, ln Vf minus ln Vi. So log m minus log n is log m by n. So log ln Vf by Vi. Okay, this is work done in isothermal process. Now see, equation of state. Okay, uh, it is in this mode. Okay, okay. Now this is the equation of state for an adiabatic process. And we say in case of adiabatic process, there is no change of heat. Now see, this is an application of the first law of thermodynamics also here. And when there is no change of heat, so the change of heat equal to 0, del Q equal to 0, right? And from the first law of thermodynamics, del Q equal to du plus del W. This is equal to 0. Now see, okay, now when no heat is exchanged between the system and surrounding, you can say when, or you take a gaseous system, suppose no heat is supplied from outside, or heat is heat goes to the outside, or heat is supplied from the outside. The change of heat is, since change of heat is equal to 0, when some work is done, by the gas, then where the energy comes? Now, the energy comes as a change in internal energy. So some internal energy may fall, right? So internal energy is a direct, we can calculate from the temperature. When the internal energy changes, the temperature changes. Okay. So now you can say, suppose there is a fall in temperature by dt, then how much energy is required for the change in temperature dt? Now that is equal to Cv dt. Cv is the energy required at constant volume for 1 degree centigrade increase of 1 degree centigrade or Kelvin increase of temperature or fall in temperature. Cv. Okay. So when this amount of energy is required for 1 degree centigrade at constant volume, but why we take at constant volume? Because in constant volume, whatever heat is supplied, that will only increase the temperature, not the external work. So Cv is the energy required for 1 degree centigrade or Kelvin. Then for dt amount, when the temperature falls by dt, because there is a fall internal energy, then du equal to cv dt, and work done, we know work done equal to pdv, del w equal to pdv, this is equal to 0, right? Now you can put in place of P RT by V, right? Here you can put RT by V. So this is RT for 1 mole, RT dV by V, right? RT dV by V equal to CV dt. Then you bring it to other side and make a cross multiplication. You will reach at this expression dt by t equal to minus ICV dv by v. If you take integration, then dt by t integration is ln t. Here dv by v integration, because RCV constant, ln v, and some constant ln k. We write some constant of integration. Okay. And if you take, if the power is here r by cv, that will, sorry, r by cv, which is multiplied with ln v, that becomes the index of v, right? V power r by cv. You take to this left hand side, that becomes plus ln t plus ln v to the power r by cv, ln m plus ln n, that is ln mn. Okay, so this is ln tv r v to the power r by cv, right? Then now you can remove using the anti-log, you can remove this logarithm, that is tv to the power r by cv equal to k. Okay, logarithm is removed. Now in place of this gas constant r, you can put cp minus cv by cv. Here cp by cv equal to gamma minus cv by cv equal to 1. So it is t v to the power gamma minus 1, right? So this is the thing. Similarly, we write the here the expression for the work done in adiabatic process, adiabatic change. Okay. Work done. Now we start with this PdV integration from V1 to V2. Okay. In adiabatic process, what we find, P V to the power gamma equal to constant K. P V to the power gamma equal to constant. This equation we find P V to the power gamma equal to constant. Okay, P V to the power gamma constant K. So P equal to K by V to the power gamma, right? So in place of P, we write here K by V to the power gamma. Hey, put him. भाई क्लास टा इवनिंग 9-10 थिला जाउछ हाँ हाँ so k by v to the power gamma dv, then we can write dv by v to the power gamma, the k by, you can take this integration v to the power gamma minus 1 and put the limit, and we will reach at this relation rt1 minus t2 gamma minus 1. Okay, with this we conclude today. And sin within So now we are going to conclude our class today. Okay.
Hello.
So
Hello.
Uday, go.
Sir, ଟିକେ ମତେ notes ଟା ପଠେଇଦେବେ କି?
So okay, try to send you.
Sir, ମୁଁ ଆପଣଙ୍କ WhatsApp ନମ୍ବରରେ ମୁଁ ମୋ ନେମ୍ ଟା ସେଣ୍ଡ କରିବି, ସେଇ ନମ୍ବରକୁ ପଠେଇ ଦିଅନ୍ତୁ।
हाँ पठेई okay.
Okay, thank you, sir.
Okay.